In this presentation, we're going to learn about using pedigrees to track human diseases. We'll learn how to identify autosomal dominant and recessive conditions and learn how to use pedigrees to calculate the probability of disease recurrence. A pedigree is a specialized chart showing family relationships. Geneticists use pedigrees in order to track individuals in a family that have a particular condition in order to determine if that condition is genetically determined. In pedigrees, we represent males with squares and females with circles. If an individual has a particular trait that we're tracking with a pedigree, we color his or her symbol dark. When two individuals mate, we join their symbols together with a horizontal line, and if they have offspring, those offspring are listed below them in their birth order. This pedigree shows a family and the presence or absence of a widow's peak in individuals of the family. A widow's peak is simply a particular shape of the hairline and is known to be genetically determined. In this pedigree, you can see that one of the grandparents on each side of the family has a widow's peak, and each of them had children, at least one of which also had a widow's peak. These women's parents both had widow's peaks. The woman on the left does, and the woman on the right does not. One of the common things we use pedigrees for is to determine whether a trait is inherited as a dominant or a recessive condition. In other words, is the allele that determines the trait dominant or recessive? One of the best ways to figure out if a condition is dominant or recessive is to simply use the process of elimination. Let's start by evaluating whether it's possible that this pedigree is of a dominant condition. We start by filling in any genotypes that we know for sure. If this is a dominant condition, then individuals that do not have the condition must have two homozygous recessive alleles. Let's call these alleles little a. Again, if this is dominant, then all unaffected individuals must have two recessive alleles. An individual that has the trait must have one allele that caused it, and that allele, in this case, is dominant. It is possible that an individual with the trait has either one or two dominant alleles. So we'll signify this by using a question mark for the second allele because we don't know whether that individual has a second dominant allele or not. Now, we need to evaluate whether this set of alleles is possible in this family. Notice that neither parent has a dominant big A allele. Therefore, it's impossible for them to pass that dominant allele to their daughter. We can therefore conclude that this pedigree is not consistent with the trait showing dominant inheritance. Once we've eliminated the possibility that this trait is controlled by a dominant allele, we can evaluate other options, which we'll do later. In this pedigree, the father and the daughter both have the same phenotype, and so we might like to determine whether this is inherited as a dominant allele. Again, we start by writing on the pedigree anything we know to be true, if this is a dominant allele. The unaffected individuals must have two homozygous recessive alleles, and the two affected individuals must have at least one dominant allele. With this written on the pedigree, we can now evaluate whether it's possible that this is a dominant allele. If it is dominant, then the daughter must have inherited that dominant allele from one of her parents. Does one of her parents have that dominant allele that they could pass to her? Yes, the father does. Therefore, we know that she inherited her dominant allele from her father, and she must have inherited a small a allele from her mother. We can therefore fill in her genotype to be a heterozygote, as we know she cannot be a dominant homozygote since she's inherited one recessive allele from her mother. So in conclusion, this pedigree is consistent with a dominant allele. There are a couple of things that we consistently see with dominant pedigrees. The first is that males and females are equally affected by the trait. All of the conditions we're looking at today are located on autosomes and not the sex, X or Y, chromosomes. We'll learn about those in the next chapter. Notice that if you have a very small pedigree, you may have only a few individuals, and they may all be male or female. Your ability to draw conclusions regarding whether it appears in both males and females equally is very limited for small pedigrees. The second feature of autosomal dominant conditions is that affected offspring always have at least one affected parent. In order to be affected themselves, a child must inherit the dominant allele from their parents. And since it's dominant, the parent must also have the dominant phenotype. You'll often hear people say that dominant conditions do not skip generations. You can see here that both generations have an individual that is affected. I don't like this idea of skipping generations because it confuses students and it leads them astray. I'll show you why later. The third feature of dominant conditions is that unaffected individuals must have two recessive alleles and therefore be homozygous. Okay, here's a much larger pedigree. Let's see whether it's possible that this is a dominant allele. We can start off by looking and seeing whether males and females are at least approximately equally affected. It looks like they are, with 4 males and 4 females affected. It also looks like affected offspring always have at least one affected parent. If we were to find a single place on the pedigree where this was not true, then we would have to conclude that it's not inherited as a dominant allele. Finally, if we needed to write the genotypes on this pedigree, we could write the homozygous recessive genotype for each of the unaffected individuals. In conclusion, this pedigree is consistent with being autosomal dominant. Let's look at autosomal recessive conditions. Is this pedigree consistent with a recessive condition? Like we did with the dominant condition, let's start by writing down any genotypes that we know for sure. If this is recessive, then we know that affected individuals must have 2 recessive alleles. Therefore, both parents in this pedigree must be homozygous recessive. The daughter, however, is not affected, and therefore must have at least one dominant allele. At this point, it may be best to just leave the second allele unknown, marking it with a question mark. So again, let's ask the question whether it's possible to be a recessive allele. The answer is that it's not, because the daughter must inherit the dominant allele from one of her parents, but neither parent has the allele to pass on to her. Therefore, we can eliminate the possibility that it's recessive. Is it possible for a daughter to inherit a recessive trait from 2 parents, neither of which show that phenotype? Again, start by writing down what we know. We know that the affected daughter must have 2 recessive alleles. The unaffected parents and brother must each have at least one dominant allele since they are unaffected. However, if the daughter is a homozygous recessive, then she must inherit her recessive alleles from somewhere. One of them must come from the mother and one from the father. Is this possible? Yes, because the second allele of both the mother and the father may be a recessive allele, covered up by the presence of the dominant allele. If that's the case, then this pedigree is consistent with being recessive. We can replace the unknown alleles with known alleles. Notice that we still do not know the second allele of the brother. He may have inherited a second dominant allele or one of his parents' recessive alleles. Since we don't know for sure, we leave it with the question mark. So let's look at some of the common features of recessive pedigrees. Again, since there are genes on the autosomes rather than sex chromosomes, males and females will be approximately equally affected. Secondly, affected offspring usually have unaffected parents. This is often referred to as skipping generations because the affected individuals will appear often generations after the trait was last seen in the family. Third, unaffected parents of affected offspring must be carriers. Carriers are individuals that are heterozygous for a recessive trait. The allele is essentially hiding in them, and they're carrying it unbeknownst to them. Finally, affected individuals are always homozygous. Let's look at how these guidelines play out in a larger pedigree. In this pedigree, males and females are approximately equally affected. In this pedigree, affected offspring do have unaffected parents. You can see this in the parents of the last generation. If we were interested in writing the genotypes on the pedigree, then we could immediately identify the parents in the third generation as carriers, or heterozygotes. We know that these individuals have a dominant allele because they're unaffected, but they also have the recessive allele because they passed it on to their children. We could also label all affected individuals as homozygous recessives. Notice that there is nothing in this pedigree that breaks the rules of inheritance, assuming that it is a recessive condition. Let's see if it could be dominant. If this is a dominant trait, then the individuals at the bottom of the pedigree must have at least one dominant allele, since they are affected. They must inherit that allele from somewhere, but neither of their parents have that allele. Therefore, this pedigree is not consistent with a dominant condition, and we can therefore eliminate that as a possibility. Let's see whether this is more likely to be a dominant or a recessive condition. If you look at the right-hand side of this pedigree, it looks consistent with being dominant. Both males and females are equally affected, and affected offspring have at least one affected parent. However, if you look at the left side of this pedigree, it's not consistent with autosomal dominant. This is because the son in the bottom left has two unaffected parents. If it was dominant, he must have a parent with that dominant allele. So let's see if the right-hand side is at least consistent with being autosomal recessive. Remember that all individuals that are affected with a recessive trait must be homozygous. All of these are homozygotes, and they only pass on the recessive traits to their offspring. Therefore, this is consistent with being recessive. Therefore, the right-hand side is consistent with both dominant and recessive traits, but the left-hand side shows that it must be recessive. I mentioned earlier that I don't like the term skipping generations. This is a good example of why. If you look very quickly at this pedigree, you would see affected individuals in each generation and would be tempted to say that this is dominant because it does not skip generations. However, you must look at it in more detail to see that it does in fact skip generations, in the sense that affected individuals may have unaffected parents. In fact, this is the better way to think about it. If affected individuals have unaffected parents, then it will skip a generation within that family and still be consistent with being autosomal recessive. A second reason why the idea of skipping generations is misleading is that if the allele is very common in the population, then many people will be affected, and it may rarely skip generations as it doesn't in this pedigree. One important use of pedigree analysis is to determine how likely individuals are to be affected by a particular trait. This pedigree is of a recessive trait. Imagine that the parents 3 and 4 want to know what's the chance that their son has inherited this trait. In order to solve a problem like this, we have to do a bit of sleuthing. We start out by figuring out whether the trait is dominant or recessive. In this case, we don't need to do that because we know we're told it's recessive. The second thing we do is to write down any genotypes that we know. We know that individuals 1 and 3 are homozygous recessive because they're affected. We also know that grandma number 2 must have a dominant allele because she is unaffected. We don't know what her other allele is. Given this information, we know that number 4 must be a carrier. We know this because she must inherit a little a allele from her father, and she is unaffected herself, so must have the dominant allele as well. Since number 4 is a heterozygote, we can draw a Punnett square like this. According to the Punnett square, there's a 50% chance that individual 5 will be affected. In this pedigree, we're interested in finding out the probability that number 6 inherits the trait. First, we can determine that this is a recessive allele because number 3 is affected but has 2 unaffected parents. Therefore, as we write the genotypes that we know, we can include numbers 1 and 2 as being carriers. Again, we know this must be true because they must each have a recessive allele to pass to their daughter, but must also have a dominant allele since their phenotype is dominant. We need to figure out the genotype of individual number 4. We know that he must have at least one dominant allele, but we don't know what the other allele is. Since we're interested in the probability that number 6 is affected, we want to know what the probability is that she is a homozygous recessive. If she is to inherit 2 recessive alleles, she must get one from her mother and one from her father. Her mother must pass on a recessive allele since she's affected and is homozygous recessive. If number 4 is to pass on a recessive allele, he must be a heterozygote. So, what we need to do is calculate the probability that he's a heterozygote, and then the probability that he passes on the recessive allele to his daughter, number 6. We can use a Punnett square to figure out the probability that number 4 is a heterozygote. Now, you'll be tempted to say the probability is 50%, but this is not correct. The reason it isn't correct is that we know that number 4 cannot be homozygous recessive because he has a normal phenotype. We therefore only consider the other 3 possibilities, and the chance that she's a carrier is therefore 2/3. Now, if he is a carrier, what's the chance that he passes his recessive allele to his daughter? Well, he can pass each allele with a 50% probability. So 2 things must be true in order for individual number 6 to be affected. First, number 4 must be a heterozygote, and secondly, he must pass his recessive allele to his daughter. The probability of him being a heterozygote is 2/3, and the probability that he passes the recessive allele to his daughter is 1/2. Since both things must be true, we use the AND rule and multiply these 2 probabilities to get a final probability of 2/6, or 1/3. Here's one last example to test yourself with. Imagine that parents 11 and 12 are interested in finding out what the chance that their newborn son has this genetic condition. When you solve a problem like this, you should assume that the condition is rare, and therefore any individual marrying into the family will not carry the disorder. For example, numbers 7 and 8 are marrying into this family, and we assume that they are normal, dominant homozygotes. To solve this problem, think about all the things that must happen in order for 13 to inherit 2 recessive alleles. The first thing is that 11 must be a heterozygote, and he must pass on his recessive allele. Also, 12 must be a heterozygote, and she must pass on her recessive allele. We want to know what the probability that 11 is a heterozygote, but to do that, we need to calculate the probability that 6 is a heterozygote and he passes on his recessive allele. The probability that he is a heterozygote is 2/3, just like in the last problem. He passes his recessive allele on with a frequency of 1/2. Therefore, the probabilities that 11 is a heterozygote is 1/3. We do the same thing to calculate the probability that 12 is a heterozygote. In order for her to be a heterozygote, number 9 must be heterozygous and pass on her recessive allele. The probability that 9 is a heterozygote is 2/3, and the probability that 9 passes on the recessive allele is 1/2. Therefore, the probability that 12 is heterozygous is 1/3. The probability that 13 is a homozygous recessive is the probability that each of the parents are heterozygotes and the probability that they each pass on the recessive allele. The probability that each is a heterozygote is 1/3, and the probability that they passed it on is 1/2 each. Because each of these things needs to be true, we use the AND rule to multiply them together to get a final probability of 1 in 36 that individual 13 will be affected.